Great, thanks, Peter. Can you hear me?
Yeah, we're a little early. You could take a minute or
Okay, let's just take a minute and let people take a quick break, and we'll start just right after 1:25. Yeah, I hope that was enough time for people to get refreshed, grab a drink of water. So we're going to kick off our first regular paper session of the conference, Adapting to the Real World. So we're going to begin with Hannah Zimmerman from the U.S. Census Bureau, and she'll be our first speaker. We'll have 12 minutes. If it seems like time might go over, I'll let you know that you have another minute to wrap up. And we'll try and keep the Q&A for the end of this session. But please enter your questions in the Q&A box as they come up, and then we'll address them at the end. So Hannah, if you want to take it away.
Sure, can you hear me?
Yep, no problem.
Okay, great. Let me begin here.
Are you able to share your slides?
I am sharing. Can you see them?
Not yet.
Okay, let me see. I don't see an option to share my slides here.
You see a green arrow, like a share button at the very bottom. Is that available to you?
I do not see that.
Let's see
okay,
if Donna, if you're permissions.
I don't think it's a permissions issue. So maybe Lisa, I think you have the slides. Could you share for Hannah? I think it might be that we're only hearing her, not seeing her video. And I'm not sure.
I actually don't have Hannah's slides. Hannah, if you could, can you email them? And
I'm gonna let me do that. Okay. Hold on.
Okay, why don't you email them, and then maybe if Sean, if you're comfortable presenting, would you be okay going while we wait for Hannah's slides?
Good afternoon. Yes, I'm more than happy to present. Can I just get confirmation you can hear me? I'm having a bit of connectivity issues.
Yep, we can hear you.
Yep, so I'm going to go ahead and share my screen. Okay, can I get confirmation you all can see my PowerPoint and only my PowerPoint? Yep. Okay,
yep,
well, okay, great. So good afternoon, everyone. My name is Sean Rhodes, and today I will be presenting on the use of farm machine data to inform establishment statistics at USDA NASS. I'd like to acknowledge my co-authors, and there's a small disclaimer at the bottom of the screen before we get started. I work for the United States Department of Agriculture, USDA's National Agricultural Statistics Service, NASS. Our mission is to provide timely, accurate, and useful statistics and service to U.S. agriculture. We produce over 400 reports annually, and data is collected from farmers, ranchers, and ag businesses throughout the year, covering virtually every aspect of U.S. agriculture. We conduct the Census of Agriculture. That's a complete count taken every 5 years of America's farmers and ranchers and the people who operate them. Similar to other national statistical offices, our agency faces various challenges when meeting our mission of providing timely, accurate, and useful statistics and service to U.S. agriculture. 3 of those challenges are declining response rates, increased cost in data collection method, and response burden. To address these challenges, a constant question is posed. Can we collect information on fields and crops for a producer without paper questionnaires or enumeration? Farming in the US is constantly developing, and especially in the field of digital agriculture. Numerous topics are contained within digital agriculture, but a few I'd like to highlight is remotely sensed imagery, global position systems, GPS, digital agriculture, and farm machine logging data. One component of digital agriculture is the flow of data from equipment to the cloud for storage and sharing. Previous research on the topic has been conducted by various disciplines. Statistics Netherlands conducted a pilot study with approximately 5 farmers to explore the use of a system-to-system approach to automate data collection for an agricultural business survey. They used an API from John Deere to have farmers share their data through the system to fill out the questionnaire. Despite the system not going into production, following the pilot study, there was significant success with the approach. Dines et al. Explored the use of machine learning and satellite imagery to estimate yields in the US Corn Belt. Results demonstrated that satellite yield maps can provide information on yield trends and inform yield gap analysis. Results of the estimation could help inform producers when using precision agricultural equipment. The novel approach we would like to present today is the comparison of values at the individual record level to historical survey data. To access machine log data, we worked with a company called MyAgData, who specializes in machine log data. MyAgData is a cloud-based application that automates data collection and reporting processes required by USDA to satisfy obligation for crop insurance and Farm Service Agency Program Participation, FSA. MyAgData applications collect, translate, and organize field-level data. In 2024, NASS conducted a pilot study with MyAgData, where 60 MyAgData producers, with their permission, provided 2023 machine logging data from 9 different states, which are included on the screen. This included 2,651 unique plant fields, 1,430 unique harvest fields. This included yield information. And the research question that we posed is, can we impute survey values with machine log data, with the goal of reducing respondent burden and survey cost? Here's a distribution of planted acreage provided by MyAgData across the US. A shade of blue represents more planted acreage, while a shade of yellow represents less planted acreage. We do have planted acreage in multiple states, but have a high concentration in Illinois and Michigan. Next is, how do we take the raw field level data and match it to the correct producer to compare survey values? Historically, NASS has stored longitude and latitude coordinates on the list frame for operators. Coordinates are from the mailing address of an operator rather than where they operate the land. Most NASS surveys focus on collecting data for a particular operation with little reference to the exact location of the land. MyAgData fields and IDs lacked any operator information to match field level information to the NASS list frame. In contrast, FSA data is heavily derived by location of the land. FSA divides parcels of land into polygons called common land units. The FSA CLU data provides the basis for one route of georeferencing. Although having a great deal of data, the CLU is incomplete. Farmers may not participate in FSA programs for a variety of reasons. Each CLU has a unique ID and can often be linked to the NASS list frame. We use the CLU as a base layer and overlay the MyAgData polygon to create a spatial join. Only certain CLUs were used to match, with inclusion criteria of the percent overlap between CLU and MyAgData polygon was greater than 9%, acres operated is greater than 1, and yield is less than 300 bushels per acre. Next, I'd like to provide some synthetic visual references. The following image shows the MyAgData polygon overlaid onto a CLU data. We can see that MyAgData polygon is close but not exact. To provide some more detail to this example, we know CLU1 is connected to NASS producer 1, and we can see the MyAgData polygon is missing 2 parts of the CLU polygon. And we have some of the MyAgData polygon overflow into the adjacent CLU. We consider this a good match between the 2 polygons. Therefore, the overlapping acreage would be assigned to NASS producer 1. Next, I'd like to show an example of a poor match. A reminder is we consider poor matches as two polygons with low overlap and small acreage. The pink polygon represents one piece of information from the farming equipment. They could have used the equipment, turned off the machine logging measurements, driven the equipment to the next part of the field, and turned the measurements back on. To provide some more detail for this example, we know CLU 2 is connected to NASS producer 2, and we see that the MyAg data polygon only captures a small piece of the larger CLU. For example, the CLU has 30 acres and the MyAg data polygon has 3 acres, resulting in an overlap of only 10%. Therefore, due to the low overlap between the two fields, these fields would not be included in analysis for producer 2. Finally, we had numerous spatial joins resulting in what we describe as a complex match. Many of these scenarios were due to replanting fields, small area of harvest, and the situation in the following image. The blue polygon represents one planting or harvesting session by the piece of machinery. This polygon covers a large area overlapping with multiple CLUs. To assign the correct acreage to the correct producer, we broke the polygon up using the CLUs. For example, the CLU in the bottom right corner is connected to NASS producer 3. The MyAg data polygon overlaps with multiple CLUs, so we would only assign a portion of the total acreage to NASS producer 3. For this example, 100 acres would be assigned to NASS producer 3 for analysis. All fields meeting inclusion criteria were aggregated from each MyAg data ID. NASS IDs that had the highest frequency and largest amount of acreage was assigned to a MyAg data ID. Of the 60 MyAg data IDs, 58 of them were able to be matched to a NASS ID. The next step is to create a given survey variable from the machine log data for a producer. To create those survey values, I've included some notation. I represents a NASS producer on the list frame. J represents a CLU associated with a NASS producer. A sub ij represents the acreage of CLU J associated with NASS producer I. X sub ij is the way that we're defining overlap percentage. That's the MyAg data acreage multiplied by A sub ij raised to the -1. And this would be bounded at 1 based on the earlier examples. Y sub I hat is the sum of the CLU overlapping acreage from MyAg data, and Y sub I is the true NASS survey values. Producers machine log data Y sub I hat, where N sub I is the total number of CLUs associated with producer I, is produced from the given equation. A general description of this equation is the imputed machine log values, Y sub I hat, is the sum of the overlapping MyAg data acreage for each CLU assigned to NASS producer I for a given crop. We use this equation to calculate producers planted and harvested variables. For yield variables, an average was taken across a producer's harvested fields. After calculating the values, 424 imputed survey values, Y sub I hat, are available for comparison in 2023. Current research focuses on the crops APS and ag yield survey from 2023, specifically on corn and soybean variables. 43 imputed values, Y sub I hat, are available to compare to NASS historical values, Y sub I. Below is a frequency table of the number of variables by planted, harvested, and yield. Next is 3 scatter plots where the MyAg data machine log values, Y sub I hat, is on the x-axis, and the true NASS historical values, Y sub I, is on the y-axis. The first plot represents planted acreage, the second is harvested acres, and on the right is yield, which is in bushels per acre. Green observations represent soybeans, and yellow observations represent corn. Overall, we can see a positive relationship associated with the machine log values and the NASS historical survey values. Now I'd like to highlight 2 conflicting observations. First is a record that has high NASS historical survey data and low MyAg data values. We believe this could be a scenario where a producer could use an outside service to help plant their fields, or they did not collect that field level data when using that piece of machinery. The second observation is a producer with high machine log data but low historical NASS data. This could be a case where they use their piece of machinery on fields they do not operate. Another potential is the piece of machinery is not calibrated correctly. And finally, the machine log data could potentially not be matched to the correct producer. For planted acreage, the scatter plot on the left, we can see there are quite a few conflicting observations, and the relationship is not as strong as harvested and yield variables. Also, there seems to be a relationship between type of crop, for example, planted acreage for soybeans. Various successes were identified during the following pilot study. The ability to compare field level data to historical NASS survey data has provided insight to the potential error or bias that would have been introduced from imputation of machine log data survey values. Some survey values line up very closely, and some have a near one-to-one relationship, implying that the methodology of our approach to compare machine log data to historical NASS survey data was advantageous. The research presented today is only on a small portion of what we could explore in the dataset. Conducting the following research presented some challenges. First is the small amount of producers' data. Receiving this data can be complex, including receiving permission and providing value added for producers to share their machine log data. Next is the conflicting observations. These observations can be legitimate due to the complex relationship the owner and the operator of the land, plus the individual collecting the machine log data. Also, we have some machine log data that we're unable to compare to NASS historical survey values. One reason is those individuals were not sampled for either crops APS or ag yield surveys in 2023, or the producer was sampled but did not complete their 2023 questionnaire. Finally, how do we scale this to a national comparison? However, with the small amount of data we do have, we have established a pipeline and a process that could be scaled to more data. I'd like to share some of the references that were used to conduct this research. And I would like to thank my co-authors once again. Also, I've provided my email address if you have any questions or you'd like to contact me about the presentation today. Thank you for your time.
Thanks very much, Sean. If anyone has any questions for Sean, please leave those in the Q&A and we'll try and get to those. And otherwise, feel free to reach out to him by email. So next up is Andrew Lifter from the USDA Forest Service at the Northern Research Station. Andrew, would you mind trying to share your screen?
Okay, can you hear me okay?
No problem.
Good. Let's see, I appear to be screen sharing over here. And we will start my presentation. I'm beginning. So you see my screen okay?
Yep, perfect.
Super.
Okay.
Hi. I work for the USDA Forest Service's Forest Inventory and Analysis Unit, where I work in a techniques development role as a research scientist. Today, I'm going to talk about opportunities for responding to changes that are coming down the pike for our National Forest Inventory System. So, many of you might never have heard of FIA, as we call it, Forest Inventory and Analysis. We're kind of like the Census Bureau, but instead of people, we measure and count trees and characterize the forests where they live. We have field and office workers who visit a set of plots that are distributed across the country, across all lands, in other words, forest, non-forest, even in water, where they measure various land and tree variables, so some of which I've listed here. There's also a lot of ticks and poison ivy, so the field workers get to experience those. So they collect those data, they get collected digitally and transferred to our database information processing and estimation folks. And then out of there, we generate reports, geospatial data like maps, other products describe the status and dynamics of the forest. The types of people who use those data are national, state, and local land managers, economists, policymakers, scientists, and they're really used to guide decisions about resource use, policy, and other natural resource related things. So I talked about these plots. Our plot design is a cluster plot, which is an array of 4 1/24th acre subplots. And yes, embarrassingly, foresters in the United States still use English units. So sorry about that. The subplots each have a 24-foot, that's 7.3 meters, radius, and the total cluster plot area is 1/6 of an acre. So our sample design, it's a spatially balanced, panelized, quasi-systematic design. Well, what does that mean? Basically, each plot, we have a base intensity. So there's one plot per hexagon. within a hexagonal tessellation of the country. In the graphic at the right, each color represents a different panel of a 5-year design. So since each panel is spatially balanced, it can stand alone when doing estimation. After 5 years, the full inventory cycle is what we call it. The full set of planned plots is complete, and the plots are remeasured. The same exact plots are remeasured starting with panel 1. And at full implementation across the whole US, 300,000 plots. That's a lot of ticks and poison ivy. So our inventory is based on a survey sampling theory. So we assume that within any subpopulation, there's an equal probability of selection of a plot for the sample. Sometimes we can't visit all of our intended plots due to safety or denied access by landowners. We have to get permission before going on the plot. So that's called non-response, when we can't visit the intended plot we meant to visit. Under our current system, we assume that any non-response occurs randomly within post-strata that we create using remote sensing data. We simply delete those plots. In other words, if it's non-response, 100% non-response, we throw it away, which is, we figured out, it's not hard to figure out, is tantamount to assigning the strata mean to each non-response plot. And then it reduces the sample size when doing the variance calculations. So it's kind of like imputing the mean, but in effect it is. And then because we've thrown the plot away, we have a smaller n, if you will. So we've known for a while that plots are not missing at random due to a situation where private landowners are more likely to forbid access to their forested parcel. This situation creates biased estimates because if it's not missing at random, the strata mean is calculated with what's left behind. And since we're more likely to not measure forested areas, we've got a problem, and that makes us sad. So how can we use remote sensing to help better deal with this, right? So the general approach, or the general paradigm for remote sensing in this case, is that it relies on the fact that the field crews measure tree and site data and a latitude and longitude they've collected with the GPS. So we bring that lat long into a GIS, a geographic information system, and we label each plot with any number of remotely sensed data layers, like satellite imagery and other GIS stuff. We then, with these newly assigned auxiliary data for the plots, we can use machine learning to impute, in other words, to model data from access plots and put them onto non-response plots using some sort of a similarity criterion. And we're going to focus on a k-nearest neighbor imputation method. So similarly, using the same whole approach, we can use a human or maybe an AI to label each plot using the context that exists on high-resolution imagery, like the USDA NAPE imagery, National Aerial Imagery Program. So it's like an augmented human approach that leverages remote sensing to label these plots with new information. So the method we're currently looking at goes like this. First, we have the imagery guy or an AI, right? They look at each plot and group them based on some sort of contextual similarity. So what do I mean by that? A human can see an image and tell the difference between an agricultural landscape and one where there are trees around soccer fields, because a soccer field's kind of rectangular and might look like corn, because it's green and square from outer space. Right? A machine learning algorithm can't tell the difference, but a human can see the people running around and the cars parked in the parking lot and the goals and label it as a soccer field. So next, for each non-response plot, we choose the 10 most similar plots with similarity determined by this k-nearest neighbor approach from each bin. So for example, here in this example, plot 6 in the forest near farmland bin that was that the AI created is non-response, and we rank the other plots in that bin based on their similarity to plot 6, and we select the top 10 nearest plots to that non-response plot in the bin. We then use a bootstrap approach to impute data onto that plot. So for example, for a given iteration, we fill in plot 6 with data from one of those 10 nearest plots. we do 1,000 realizations of this bootstrap approach to get 1,000 complete data sets. I've just shown 3 here, but you get the point. Plot 6 has different numbers for each of the iterations here. We then can calculate 1,000 means of the complete data set and 1,000 variances of that complete data set. So finally, we can calculate the the grand mean. The mean of the means becomes the grand mean, and the variance of that grand mean is a combination of the mean of the variances and the variances of the means. It's kind of hard to say that multiple times. The combination uses approaches that are described by Rubin. A lot of you are probably familiar with, and I'm sure the multiple imputation guy who talked earlier today, I love the talk, by the way, that Rubin described in his 1987 book. Paul Van Dusen, a colleague of ours who passed away somewhat recently, and he was a great guy, wrote about this in 1997 in the context of forest inventory data. For some reason, it was never adopted. And I was kind of surprised when I found this. I'm like, oh, wonder why we're not doing this. And I think it was probably because it was very hard to operationalize back then. But the point is, doing this approach would really fix some of the bias we've been observed by leveraging remote sensing and imputing, instead of the straight mean, better data, better information using the remote sensing onto the missing plots. And then we won't feel sad anymore. So most of us, or many of us, have the good fortune of having budget cuts coming or greater restructuring. So taking this paradigm a step further, this has gotten some of us thinking. The proposal in the current president's budget, and this is just online, I'm not revealing any secret information here, is that they want to, the proposal is to double the length of our inventory cycle. In other words, instead of a 5-year cycle like we might have at the top that people are used to, our customers are expecting, we go to a 10-year cycle, such that in 5 years we'd only have half as much information, half as much current information with which to make the estimates. And that could make some of the people who are, who's rely on a certain data flow, on a certain periodicity of the results, that might make them sad. But, being a scientist and being creative, we got to thinking, gee, well, we could use this non-response mitigation paradigm that I described. Maybe we could treat those red plots, the ones that are going to be missing, as non-response. And we can do a similar multiple imputation approach to make pink plots which are modeled based on the green data. So that is something that I think that we're going to be exploring, depending upon what happens in this summer with all the reorganization business. And another approach that comes up, but using that same paradigm that I've articulated, is that maybe we could measure the plots at time 1, right? We got the field crews out there measuring the trees, but if the combination of the contextual AI and machine learning confirm that the plot's just been chugging away, no big changes, in other words, hasn't been cut, the trees haven't died, they're just slowly growing in a very stable way, maybe we can model the tree attributes at time 2. So that means we in an intelligent way choose which plots we're going to revisit and remeasure. So we save money by avoiding these field visits on plots that are unlikely to have changed in important ways. So those are 2 options for dealing with the situation we currently find ourselves in. So the current status of this approach, and specifically about the non-response mitigation approach, is that we did this, we executed the entire procedure I described on the Honduras National Forest Inventory data with colleagues in Honduras, because in the old days, the before times, we used to do tech transfer with our partner countries. So we learned how to do this with their data. And we have an estimation system we programmed with their data, which we can then transfer. One of the benefits of that kind of work is we transfer it to our current situation. Second, we're comparing this approach to alternative non-response mitigation techniques using real data. Next thing we need to figure out is, is KNN the best way to go here? Those of you who have done KNN and compared it to other machine learning algorithms, often not as accurate as something like random forest or neural networks. So we need to look into other imputation approaches beyond k-nearest neighbor. And finally, we need to get feedback about our pink estimates, the partially modeled and partially real estimates. Does their pinkness impact their use by our decision makers? With that, I'll end and yield the floor. Stop sharing here. I don't know if anyone, am I still connected?
Excellent. Thanks, Andrew. That was really delightful. I appreciate all the graphics.
I do what I can.
Nice work. So if anyone has any questions for Andrew, please pop those in the Q&A and we'll get to those at the end of the session. Next up, we have Rashi Saluja from Westat. Rashi, can you share your slides?
Yeah, just a second.
And we can hear you, by the way, no problem.
Oh, can you see my screen?
Yep. So whenever you're ready.
Perfect. Just show this. Hi, everyone. I am excited to share our work on using machine learning and diverse data to boost respondent incorporation in surveys. This project is a collaboration with several wonderful colleagues, and today I'll walk through the approach, findings, and what they could mean for future data collection. I would like to start by stating the growing challenge of declining response rates and rising costs in survey research. Despite outreach across multiple modes like text, phone, email, it's getting harder to connect. And one underused resource is paradata, the digital footprints of our contact attempts. And the question we asked ourselves was, can we use these patterns in paradata to build smarter and more efficient outreach strategies in surveys? And while we asked these questions, we got to our three main goals here. The first one was to use machine learning techniques to detect patterns in paradata. The second one was to group the households in surveys with similar contact response patterns using something like clustering. And the third one was to translate those insights into practical strategies for more effective follow-up and response rate. So for this project, we have worked with data from Medical Expenditures Panel Survey, or MEPS, specifically the household component. MEPS is a nationally representative survey designed to track healthcare use and expenditures across the country, and it plays a vital role in informing health policy. The survey is conducted by Westat for the Agency for Healthcare Research and Quality. And what makes MEPS unique is its sample design. The households are drawn from the National Health Interview Survey, which provides a rich demographic baseline. And we also enriched this data set with demographic data from American Community Survey and Advanced Call records. So we specifically focused on data from spring 2022 round 1 of MEPS. And in this round, there were over 10,000 sampled households. And we narrowed our analysis to about 8,600 households that had at least 2 contact attempts made to them. Out of these, roughly 4,700 households completed the survey, while about 3,900 did not. So this gives us a completion rate of around 54%. And I think this is a mix of complete and incomplete cases was useful for identifying patterns in distinguishing responders from non-responders. And each household's record includes a sequence of contact attempts, their modes, and their outcome. So the plot on the right here shows each row as a household, and then each colored box here represents the contact attempt. It can be phone call, text, an email, or an in-person visit. The rows are sorted by how many contact attempts each household received, and from most at the top to fewest at the bottom. You can see some households received over 50 contact attempts, while others reached just a few. And one main insight here can be there are a lot of greens, that means complete contact attempts made when the contact sequence is really low. And while we move up as contact sequence increases, there are a lot of reds indicating incompletes there. We did then apply an unsupervised machine learning method called clustering, and clustering helps group similar households together so we can find patterns in how they respond without needing to label them in advance. We looked at each household's contact history as a sequence. So for example, first they got a phone call, then a text, and then an email. So that will be their contact sequence. To see which households had similar patterns, we used a method called optimal matching. It compares two sequences by counting how many changes it is needed to make one sequence turn to another, like by adding or deleting or switching steps in between. Then we used the clustering algorithm called PAM, which is partitioning around medoids, which groups together households with similar sequences. And this helps us find natural patterns in how different households are contacted and how they respond. These are the clustering results. We identified 5 clusters with different response profiles. Cluster 1, as you see here, performs really well with 64% complete rate, and it's associated heavily with telephone contact. You can see a lot of yellows, which indicate the telephone contacts here, and it seems to work well for this cluster 1. Cluster 2 has moderate completion, 44%, and shows a variety of contact modes, a lot of purples, which indicates in-person visits. And these households may be more neutral in how they respond. There is a mixture of reds and greens here. Cluster 3 and 4 have lower completion rates, 27 and 30%, and require large contact attempts. Cluster 3 shows a lot of yellow. That means telephone sequence and longer contacts. And cluster 4 shows in-person visits and longer contacts. Cluster 5 here looks like our ideal cluster. It has the highest response rate, 72%, and it represents our most successful group. These households respond quickly and often have a fewer contact attempts. The green bars here, like a lot of green bars, show the complete attempts here. So now, after the clustering, we do wanted to differentiate these clusters based on the demographic data that we had. To get insight on how these clusters differ demographically, we used multinomial logistic regression to explore how demographics relate to cluster membership, and cluster 5 served as our reference group. The plot on the right here shows how well the model performed across different levels of complexity. On the bottom, we move from a very simple model on the right to a very complex model on the left. And the vertical axis here shows the error. Lower means better performance. Each red dot here shows the average performance, and the bars around show the uncertainty. As we move from right to left, the error first goes down, meaning the model is improving until it reaches its lowest point and then starts to go up again, which just shows that the model is being too complex. We chose the model near that low point where it performs the best without being overly complex. The aim was not here to be predictable in terms of model, but the model should be generalized enough to have differentiating features based on our clusters. We chose statistically significant features that came up, like participation, mode of entry, language, and race. You can see 4 of them here. The reference here is again cluster 5. The positive coefficient for participation means the cluster is associated with more likely participants, while negative coefficient means the cluster includes more households that are less likely to participate. Since the coefficients across clusters for participation variables are slightly positive, we can say that compared to cluster 5, the other clusters include households that are just a bit more inclined to participate, though the differences aren't very large. But when we look at feature language and we see English and Spanish speaking households, these bilingual households in cluster 1 and 2 have strong negative coefficients, meaning these households are much less likely to be English and Spanish speaking compared to cluster 5. Similarly, for mode of contact, cluster 2 stands out with a strong negative coefficient, suggesting it has a lower exposure in terms of outreach compared to cluster 5. And for race, clusters 1 and 3 show noticeably higher coefficients for Asian respondents compared to those in cluster 5. The other thing apart from coefficients that can be stated important here is the predicted probabilities. And we have some graphs for predicted probabilities for different features. The first one is for age, and we have compared each cluster with cluster 5, which is our ideal cluster. It shows how age relates to the likelihood of a household falling into different clusters compared to cluster 5. So in cluster 1, older households or older adults are more likely to be in that cluster than younger ones. In cluster 2, the probability decreases with age. Younger people are more likely to fall into this lower response group. For cluster 3 and 4, generally show low predicted probabilities across all age groups, with a slight drop in the middle-aged group. If we look at the predicted probabilities by race, we can see that white participants are most likely to be classified in cluster 1 than cluster 5. And similarly, participants with multiple races are more likely to be classified in cluster 3. Cluster 4 shows uniformly low probabilities across all race groups, suggesting race is not a strong differentiator when compared to cluster 5 for cluster 4. If we look at the mode of entry, your mode of entry is described by 3 labels. The MFOS, which is just simply means that it was entered via a mobile phone. The SMS, submitted through the study management system, or the IMS, entered on laptop through the IMS interface. We see that households in cluster 1 are likely to be entered via SMS. In cluster 2, they are likely to be entered by MFOS, that is by mobile. In cluster 3 and 4, there's generally weak engagement across modes. And lastly, when we look at predicted probabilities by participation, we see that cluster 1 being more common among people who are eager to participate, and cluster 2 being more common among people who are hesitant to participate. When these are some of the potential data collection strategies that we came up with. So what can we do with all of the insights that we found? We can use cluster information to tailor the outreach and use different contact strategies for different clusters based on their response patterns. Or we can reconsider sequencing. Maybe SMS first works better for some groups, but phone first works better for others. Also, the next steps include refining our clusters with new data, testing the targeted outreach that we discussed, and building dashboards for real-time tracking. Eventually, we hope to pilot a dynamic contact strategy that adapts as information comes in. And we are excited about these next steps, and hopefully we get to share more results on this as we progress. Here are our contact information if you want to reach out with questions, or if you're working on similar projects or tasks, I would love to connect. And thank you for your time. I'm not sure.
Thank you, Rashi. So next up, we have Emily Malfino from the US Census Bureau. Emily, will you turn your camera on and share your screen?
Great. Yeah. Can you hear me?
Yep, no problem.
And can you see my slides?
Yep, perfectly.
Fantastic. So thanks for listening here to me today. So I'll be talking about the Open Census Initiative at the Census Bureau. So there is increased federal action on promoting transparency in federally funded research through open science. So on the screen is the definition of open science for the federal government. We also see this in recent actions like a 2022 memo from the Office of Science and Technology called the Ensuring Free, Immediate, and Equitable Access to Federally Funded Research that has a focus on research in peer-reviewed journals and even recent executive orders with a focus on reproducibility and clarity. So there are many federal agencies leading the way with open science practices and repositories, to include the Department of Energy and the National Institute of Health. So while federal statistical agencies are in the process to catch up, there is a lot we can learn from these other agencies. For example, their repositories for data and research share common characteristics, which includes the use of standardized metadata and the use of persistent identifiers. In fact, much of these characteristics are now requirements laid out by various memos and executive orders. The Census Bureau is certainly not starting from scratch. Many in the Bureau have already been practicing open science principles and best practices. Yet there are some hurdles. For instance, the current dissemination platforms reduces the benefits open science can bring. So the Census Bureau leverages a broad number of locations to release and publish data and research output. Some of these are listed here, but not all. Current platforms are disparate with minimal interconnections. Users must go to several different locations to make connections between research output and data themselves. It often requires knowledge of Census Bureau structure and jargon, and research becomes harder to find as time passes. And additionally, they do not meet requirements laid out by that OSTP memo or other OMB guidance, such as the use of persistent identifiers or standardized metadata. Now, ultimately, this makes it difficult to understand how data and statistical products are used once disseminated to help promote the reuse of our research. The Open Census program will make federally funded research, code, and data readily accessible and transparent, fostering a collaborative environment that promotes innovation. We will be working with others, both within and outside the federal government, so that Open Census incorporates open science best practices. Now, Open Census will go beyond what is included in that original OSTP memo. That memo was only for traditional peer-reviewed work and related scientific research data. Open Census includes a wide range of research output to include working papers, research code, statistical software, and so forth. Now, Open Census involves three distinct but connected efforts. Open Science aims to improve access and discoverability of publicly supported research output like white papers, technical reports, code books, journal articles, and conference presentations. Open Code aims to facilitate access to and collaboration on Census Bureau statistical software and research code. This effort covers code such as research code that support working papers, code for intermediary results in research, the sample code on how to use microdata, and software such as linking programs. Open Data aims to support access, discovery, and reuse of Census Bureau statistical products, which includes incorporating commercial cloud data repositories to release and access Census Bureau data and assigning persistent identifiers to our statistical products. Connecting this all together is standardized metadata and persistent identifiers, which will also support discoverability and archiving. Now, there are several parallel efforts looking into metadata internally at the Census Bureau and within the Department of Commerce and within the federal government. And we will be utilizing existing metadata schema that align with these efforts. Now, diving in a bit into these three efforts. So first, open science. The goal of open science is to provide a centralized location where research output and metadata can be released, easily discovered, and seamlessly interconnected. To do this, we aim to develop a Census Bureau solution for an open science repository and incorporate new metadata, such as persistent identifiers for the artifact, organization, and researcher, while providing pre-built citations. This will increase the visibility, recognition, and impact of Census Bureau research, while also strengthening Census Bureau's archiving practices. The goals for open code is to facilitate the dissemination of software products and code to increase understanding and transparency of Census Bureau research. We will be leveraging GitHub here and developing guidance and best practice around the use of GitHub and disseminating code. So open code will increase the transparency of our research process, and more on this later. Open Data's goal is to provide platforms to release, discover, access, and improve metadata that support data discoverability and reuse. This includes, as I said, creating cooperative agreements for cloud-supported downloads, like with AWS Open Data, and assigning persistent identifiers, like digital object identifiers for our data, and aiding with data discoverability through metadata. The benefits of open census range from increased transparency, which ensures research findings are open to scrutiny and validation, to promoting accessibility and collaboration, which fosters a more participatory research environment, to reusability, which makes research more efficient, to increase visibility, which broadens the reach and impact of Census Bureau work and research. So this brings me to the future state of open census. This figure depicts the research publication process under open census. And don't worry, I will zoom in on the different parts. So ultimately, open census will provide structure and clarity around the census publication and data processes, and develop and communicate guidance around the new open census requirements. So I'm going to be moving from left to right here. So researchers will continue to produce the great research they already do, and program areas will continue producing the publication series. However, they will be able to create more supporting artifacts, such as research code or research data, with the knowledge that these will be easily discoverable and accessible alongside of their publication. Researchers will be able to add their unique ORCID ID to go along with publications where their names are attached, which help facilitate the automated linkages between a researcher and their research output. From there, open census really gets going. Digital object identifiers, or DOIs, will be assigned to products, and persistent identifiers will be aligned. Researchers will work with designated staff to meet the expanded metadata requirements. Now, we don't want open census to be viewed as a burden within the Census Bureau, and that is true with the expanded metadata requirements. Rather, open census is an opportunity for researchers to expand the reach and impact of their hard work. With the expanded metadata, researchers can see increased visibility of citations, greater ability to see how their research artifacts are used once disseminated, and increased transparency and replicatability. Open census will streamline dissemination platforms by providing a centralized location to discover Census Bureau research output and see connections between research code and data. To wrap up, in the near term, we are socializing open census. We have developed a concept of operation, of the vision and operation of open census. We are working on updating standards and gathering best practices around open science, and you'll see two of these efforts shortly. From there, we'll be building out the open census platforms and updating publishing processes. And in the long term, Open Census will just be integrated into our everyday research processes. So I do want to highlight 2 current activities. One is around guidance on how to cite statistical products. So on census.gov, we have replaced the page that was originally called How to Cite Our Internet Information with actual guidance on how to cite our data, tools, technical documents, and research. And I could put the link in to that page in the chat once I'm done with this presentation. This guidance includes examples on how to cite for a range of different types of products. We designed this information based on guidance from other statistical agencies and our own subject matter expertise. The focus here is not on a particular citation format, but on the components the citation should have. And this information is evolving, it's living, and it will evolve as persistent identifiers are adopted and if new products require additional guidance to be created. And this has not been our final step. We adapted this guidance for Census Bureau researchers on how to cite restricted data. And this guidance is available to Census Bureau researchers on our internal SharePoint. So restricted data are data that are made available to approved researchers and projects for statistical purposes. So they require a slightly different way to cite them. So the guidance we developed kind of helps address this unique case. And I've been working with the FSRDC, the Federal Statistical Research Data Center Network, to update this guidance for our researchers accessing Census Bureau data within the research data centers themselves. We are also creating guidance for Census Bureau researchers on GitHub and becoming members to and sharing code on the Census Bureau GitHub page. So this guidance will include information on writing clean code, access, content, membership, license language, archiving, etc. This guidance is in the final stage of development and review, especially around the licensing language. But we hope to be able to release this guidance internally to Census Bureau researchers really soon. So that we can start facilitating the more dissemination of research and statistical code publicly in our GitHub. And from there, Open Census will also facilitate clean code brown bags, because as many as you know, in order for code to be transparent, it also must be easy to read, understand, and maintain, especially if we're releasing code that we have used internally in our research. So Open Census will help facilitate some of these brown bags internally. So ultimately, Open Census will help Census lead the way of open science in the federal statistical space. And with that, thank you very much.
Excellent. Thank you, Emily. So we'll now move to our last speaker. So we have Hannah Zimmerman from the US Census Bureau. We had some technical difficulties earlier, but Hannah, would you mind trying to share your screen?
Can you hear me now?
Yep, we can hear you, no problem.
Okay, great. So let me get this going.
Perfect.
Okay, sorry, I'm having some technical difficulties. Let me load this. Okay, well, least but not last, good afternoon. My name is Hannah Zimmerman, and my co-author for this research project is Ellis, who is also present. We are excited to participate in the GASP 2025 conference. The title of this presentation is Automating Multilingual Census Data Processing, a transformer-based pipeline for efficient language detection and translation for short text. Without further ado, let's get into the agenda. So the agenda laid out for this presentation begins with an introduction to the race and ethnicity responses on the decennial census, an introduction to the race and ethnicity autocoding, addressing the census short text challenge, We will then move on to new pre-processing techniques to come out of this research. From there, we will get into the automating of translations for the non-English write-ins, which includes utilizing AI and transformer models, encoding, embedding, and validation via cosine similarity, and name entity recognition near-like systems, leveraging semantic similarity metrics, and evaluating model performance. I will then wrap this up for you with a conclusion and some future work. Okay, so let's start off with the introduction. The 2020 Decennial Census collects responses to open-ended questions on race and ethnicity, which allow individuals to describe their identities in their own words. On the right-hand side, you will see an excerpt of the Hispanic and race origin questions found on the Decennial Census. Both questions allow the respondent to elaborate and write in their identities. I have also included examples of the non-English write-in responses so you get an idea of the width and breadth of the short non-English write-ins. These are not real responses, but just illustrations. This research focuses on these non-English write-in responses submitted through the Internet Self-Response platform in one of 12 supported languages. And in order to be included in official data products, these responses, their language, must be accurately identified, translated, and standardized to align with the Census Bureau's race and ethnicity classification system. To understand the challenge, let's look at the current process of race and ethnicity processing. Non-English write-in responses from the Internet Self-Response Platform, ISR, involve a three-step process. First, the language identification is done using the Apache Tika computer program, then human translation of languages, and then finally auto-coding of the translated responses. However, several challenges arise during this workflow. The system's limitations in accurately processing short responses, incorrect language identification causing misrouting to the wrong translators, backlogs in translation because of high demand and limited translator availability, and of course, human translation is expensive. Table 1 shows that Apache Tika is particularly confusing languages with lexical similarities, resulting in misrouting and increased translation workloads. We see that between the Japanese and Chinese languages, these challenges become the impetus for our research into new pre-processing and processing techniques of this niche short English race and ethnicity write-ins. And this leads to our problem statement. How can short non-English race and ethnicity write-in responses from census surveys be automatically detected, translated, and auto-coded using natural language processing and AI models, such as transformer-based language models, to reduce misclassification, manual processing, and backlogs, while improving accuracy and efficiency in race and ethnicity data processing? This project started with a deceptively simple but high-stakes question. How can we improve the processing of short non-English race and ethnicity write-ins from surveys? Many of these are short non-English responses. They're often just 1 to 3 words. This makes them really hard to process. Language ID models usually perform well on long text, especially those that use full characters. Those language ID models that perform well on long text, but they struggle on short phrases, especially those that use few characters or are misspelled. That causes misrouting and sends responses to the wrong translator. Meanwhile, high demand, limited translator availability, and the cost of human translation have created delays and backlogs. And this is only growing. We're seeing more short-form text behavior in our surveys influenced by platforms like Twitter or TikTok, where brevity is the norm. So our goal was to design a multilingual AI and transformer-based pipeline that can accurately detect language and translate, especially short write-ins, automating and reducing misclassification, human burden, and lag. This is what I'm going to walk you through today in this presentation. New pre-processing techniques. What I am presenting is a pre-processing technique that deals with eliminating misidentification of short non-English languages. Like I said, IDing the language of short non-English text is not an easy feat, and while many models can detect the language in more scripts and full sentences, many fail at 1 word, or few character write-ins, ergo the majority vote language detection system. The majority voting system integrates 3 sources of language detection: 2 probabilistic language predictors, fast text that IDs 170 languages, and XML Roberta, which only IDs 20 languages. But we also have a strategic use of paradata, that is Lang ID. That's the user instrument language selection. Also, since research shows language detection models perform better with longer inputs, shorter texts were repeated to reach 100 characters. And as the name implies, the system processes the text through each model, gathers predictions, and counts the votes from each source. The language with the majority of votes is selected. If no clear majority is found, the system applies specific logic to handle edge cases. As Table 2 shows, for the Japanese language, it accurately detected the language 100% of the time, even correcting mislabeled cases that were in fact Chinese. The majority vote system was consistent in detecting the language even for low resource languages such as Tagalog and Haitian Creole. Once the language was identified, we could see how frequently certain write-ins would show up in the paradata write-ins. It turned out that it was not a simple matter of matching non-English write-in responses to common pre-established translations. Figure 1 shows that 94.8% of Japanese write-ins fall into the low frequency category. That means they're nuanced. To reduce manual processing and backlogs, we needed to test AI translation models. Automating translations. A dual model translation system for short text was implemented. 2 models were used for translations: Google MATLAB and the No Language Left Behind, with 200 languages in a single AI model. While MATLAB performed well and sometimes even better for some languages like Arabic without prompting, No Language Left Behind required contextual prompts in the identified non-English language to refine output accuracy. I have included an example of the prompt for Japanese and its English translation. These were appended to the write-ins. Figure 2 shows a 96.5% reduction in manual translation that would be needed for most languages. The red bars show that overwhelmingly, the models were able to translate most of the workload. That means they can reduce translation backlogs by accurately handling short text, low research languages, and dialects in near real time. This drastic decrease underscores the effectiveness of automated translation models in handling the bulk of translation needs, freeing manual translation staff to focus on outlier cases, those in blue, that require specialized knowledge or intervention. This demonstrates the benefits of integrating advanced AI translation techniques into the census translation workflow. Once we have a translation, we still need to know, did the model get it right, and is it in context? This is where we lean on both the Census Bureau's classification system and cosine similarity. By embedding both the translated responses and the Census Bureau's historical corpus of race and ethnicity classifications using a sentence transformer model, we can compare them using cosine similarity. This allows us to validate, standardize, and even clean noisy translations in near real time with results ranked by the similarity. In other words, the embedding and the similarity process forms the backbone of a lightweight named entity recognition near-like pipeline, one that works based on meaning, not just pattern matching. So what is encoding? Encoding is how we turn words into something a computer can understand, while embedding gives those words meaning by placing them in a space where similar meanings are close together. That's how we can detect, for example, that Mexican American and Latino are closer in meaning than something like Canadian. Here's a flowchart of the process I have just described. We embed and encode the model's translations and the Census Bureau's historical corpus of race and ethnicity classifications using a sentence transformer model. We compare them using cosine similarity. Results are ranked by their similarity scores, and this allows us to validate, standardize, and even clean noisy translations. Since for each short text response, we generated 2 translations, one from No Language Left Behind, one from MATLAB. Instead of choosing arbitrarily, we compared them to each other using the all mini-LM sentence transformer model. Whichever translation had the higher semantic value or was more complete, like American over America, was selected as the preferred version. If the models closely agreed, like a score above 0.50, we made automatic or direct selections. If the score was below our threshold, it went through logic review. If that logic failed, it meant that the models diverged significantly, and we flagged the translation for human review. This helped us make smart, consistent decisions, trusting the models when they aligned and catching errors when they didn't. This scatter plot shows how translations across languages compared using semantic similarity scores. These scores tell us how close 2 translations are in meaning. The distribution of similarity scores varies by language. Denser clusters in the high similarity zone suggest that the model performs very well for those languages. However, languages with more low-range scores like Arabic or Indo-Chinese may benefit from prompt tuning or additional methods for improvement. In this last step, we compared model-selected translations against human-provided gold standard translations. The goal is to evaluate how well the pipeline aligned with human interpretation across languages. The average semantic similarity scores you see here represent how close in meaning the model's translations were to human ones. For example, for Japanese and Portuguese, scores were over 0.91 and 0.96, which is very high. Overall, this suggests that our system produces translations that are fast and automated, and also closely match the intent of human translated responses. This kind of benchmarking helps build confidence in AI-assisted workflows while still highlighting areas like Arabic or Chinese, where further tuning or human oversight might be beneficial. So I'm wrapping this up with our conclusion. This research was dedicated to enhancing the accuracy of language detection and the efficiency of translating race and/or ethnicity write-ins by deploying AI models within a structured translation pipeline. These innovations, coupled with the strategic use of paradata and contextual prompting, have led to substantial preliminary reductions in misclassification rates and manual translation workloads. Improvement plans follow to include different models and filters for each language, and using the lang ID to determine which language-specific path and incoming text should follow. For instance, a plan is in place to extend the current majority vote ensemble, fast text, and XML Roberta into paradata with the following steps: to benchmark and include LSTM-LID. This is the long short-term memory for language identification. It is a script-aware character-level model designed specifically for short text language identification. This is to make that ensemble more robust and to limit edge cases. A process will also be established to add multilingual spell checking using rule-based and machine learning models to correct typos based on both word count and surrounding context. And with that, I leave you and I wrap up this presentation. If anyone has ideas on how I can improve this translation pipeline, please do email me, and I'm open to taking questions.
Great, thank you, Hannah. So we've received a number of questions in the Q&A box, and we can go through some of those. I'd encourage folks to leave more questions in the Q&A box if you have any, because we still have a few minutes to cover those. And especially panelists, if you have questions for your fellow panelists, please feel free to chime in with those. So in lieu of fresh questions, I was hoping our panelists could maybe take a second to talk about some of the replies they gave. So first up, Emily, if you want to comment on the questions you received, about whether you provide training on Git, metadata, and so on within the Census Bureau or for external users.
Yes, so in regards to training, there are many programs already and program areas already use Git in their everyday research or production cycles. And they, depending on the program area, provide their own training internally to their team. However, I talked about in the presentation, in the future having clean code brown bag. So discussing how to write code for public dissemination. And that will incorporate Git practices. Just because something is written on Git does not necessarily mean it's ready for public dissemination. There's a lot of other documentation and cleanup that has to happen. So the two are interconnected. And I put this in the note, is I could also maybe envision a repository in our Census Bureau GitHub that talks about some of our best practices to help with an education outreach would be a really good idea.
Great, thanks for commenting on that. And then there's another question from Peter Mayer about, do you anticipate partnering with specific data users like OpenStreetMap,
Yes.
Wikidata, or libraries to set them up to cite census in the best way using your DOIs or other tools?
Great idea. So we have starting down that effort. Is that I have been working with different organizations that manage organization IDs. So this is Wikidata, ROAR, ISNI, and they have these are persistent identifiers for organization. So it's the Census Bureau, and each one of these has an organizational ID. And I've been working with them to make sure that our information is up to date and accurate. And that's one step, especially around in Wikidata, is if Wikidata doesn't have updated information on the Census Bureau, then those using Wikipedia and citing Census Bureau data won't have updated information. So first step was updating our organizational IDs. Next will be using for our ORCID IDs, which are for the researchers, and that also uses organizational IDs. So that was one step, but I do like the idea of working with, especially these open source collaborative efforts around the OpenStreetMap and Wikipedia. So they're collaborative, they're open source, and having specific documentation on how to cite census, so it's consistent across the board. And it's a really good idea. We do have efforts within the Bureau, such as the Statistics in Schools, I think it's called, and other outreach dissemination efforts with a dissemination specialist that work with libraries and work with schools. So I'll be working with them to make sure that they know about the citation guidance so that they can start kind of education, and I'm hoping kind of spread this knowledge out.
Well, thanks so much. So I'm going to take a second to, if Rashi, if you want to respond to a fresh question in the Q&A. The question is, what is the logic for comparing all the clusters to cluster 5? Could you instead just look at probabilities within each cluster, or is there another option you considered?
So the main reason why we chose cluster 5 as reference in multinomial logistic regression was cluster 5 was our ideal cluster. It had smaller contact sequences and high response rates. That is why we wanted ideally every cluster to move towards cluster 5. That is why we set that as reference and see coefficients and predicted probabilities accordingly.
Great, thanks, Rashi. And then last up, we have a couple questions that came in for Andrew that I'm hoping you could maybe take a minute to comment on. One of these questions was asking, to what degree do you think these machine learning imputation tools will decrease the need to actually survey? And the commenter says they imagine there's a limit to how accurate machine learning can be as actual survey data decreases.
Right. I don't remember what I wrote. Yeah. So the machine learning, okay. In order to make these synthetic estimates, you're counting on there being a good relationship between the auxiliary data used for the prediction and the thing you're interested in on the ground. In forest inventory, there's a lot of attributes that are of interest that aren't really amenable to, using remote sensing data to make estimates. For example, the number of dead red maple trees in a 30 by 30 meter area. the satellite really isn't going to be able to see that. Right. So you could do a k-nearest neighbor or some sort of a fancy neural network, and you're never going to get a good estimate. So if the auxiliary data don't have a strong relationship with the thing of interest, that this kind of falls apart. And then secondly, like you're alluding to, you could say, oh, what if we only measured 10% of the plots and 90% of them are non-response? Well, those 10% happen to be just a bad sample, right? Bad set of training data, and they don't represent the full spectrum of conditions on the landscape. We could build a model and push our run button and generate our tables, and they could just be completely wrong. So there's some kind of a balance between how well represented the area of interest is and the number of training data, the accuracy of the results. So
Thanks.
I know I'm kind of babbling here.
No, that's a nice wrap up for the kinds of things
Okay.
we're talking about. So with that, I want to thank all of our presenters. I appreciate the talks you gave and your flexibility with dealing with inevitable technical challenges. And we'll move on to the next session. Thanks so much, everyone.
Okay, so